I want you to try something for me right now. If you're in a place where you can do this without looking strange, take a second and look at the tag on your shirt or, your pants. Just check the fiber content.
I'm going to make a prediction here. It says polyester, or maybe nylon,
Yeah.
or if you're really unlucky, acrylic.
Right. If you are like the vast majority of people listening
Ooh.
right now, the answer is yes. We are literally walking around wrapped in plastic, and usually we just don't think twice about it. I mean, it's just clothes.
Exactly.
But I was looking at the data we have for this deep dive, and the scale of this whole plastic clothing economy is actually terrifying.
It really is massive, and it's growing at a rate that is, frankly, hard to wrap your head around. If you look at the period between 1975 and 2018, global fiber production didn't just double, it quadrupled.
Wow.
Yeah, we went from producing about 24 million metric tons to over 105 million metric tons annually.
That is a staggering amount of material, and I assume most of that isn't cotton or wool.
No, not at all. The hidden cost of that explosion is a really heavy reliance on petroleum. We are talking about high pollution levels, massive energy consumption, and the release of microplastics.
Right.
The estimates we're looking at suggest anywhere between 4.8 to 12.7 million tons of plastic debris are entering the ocean every single year.
It's interesting you mentioned the ocean and debris because I think when we talk about plastic waste lately, everyone has this very specific image burned into their brains from the last few years.
The masks.
Yes, exactly. Disposable blue masks and latex gloves littering the sidewalks during the pandemic.
Right, that is a great point. And the data on that is actually quite surprising. It completely challenges our intuition. There was this huge panic that personal protective equipment, or PPE, which is completely overwhelm our municipal waste systems.
I mean, it felt like they were carpeting the streets in some cities.
Visually, yes, they were very obvious. The issue there was dispersal, people just dropping them where they shouldn't. But when you look at the hard numbers in terms of pure volume, masks and gloves only accounted for about 1% of municipal solid waste.
Only 1%. Really?
Yeah, just 1%. The real surge in waste during that time came from the general rise in single-use plastics, packaging, online shopping materials, food containers. That is the bulk of the iceberg.
So the problem isn't just the medical waste, it's our everyday consumption.
Precisely.
And that really brings us to our mission for today's deep dive. We are looking at the textile industry's attempt to solve this massive plastic problem. Today, we're talking about biopolymers.
Right, moving from a take-make-waste linear economy to something circular.
But I want to be super clear before we start. We are not here to just read the marketing copy. Every brand today claims to be eco-friendly or green. Our goal with the source material today is to look at the chemistry. We want to really understand the science of replacing oil-based plastics with materials made from corn, bacteria, and this one I'm really curious about, crab shells.
I know, it sounds like science fiction, but it's material science. And as we'll see, it's much more nuanced than the headlines suggest.
So let's start by clearing up the confusion, because I think this is where 90% of consumers just get totally lost. I see a tag on a shirt that says bio-based. My brain immediately goes, great, I can throw this in my compost bin and it'll turn into dirt. But looking at these notes, that seems to be a pretty dangerous assumption.
It is arguably the single biggest misconception in the industry right now. We have to be incredibly precise with our language here.
Yeah.
Bio-based and biodegradable are two completely different concepts.
Break that down for us.
So bio-based refers to the origin of the carbon. Did it come from an oil well, or did it come from a plant?
Okay.
Biodegradable, on the other hand, refers to the end of life. How does the material behave when you throw it away? Does it actually break down in the environment?
And the sources are telling us you can have one without the other.
You certainly can. The biodegradability of a plastic depends entirely on its chemical structure, not where the carbon came from. For example, you can take ethanol from sugarcane, which is a plant, process it, and turn it into polyethylene, or bio-PE. Chemically, that molecule is completely identical to the plastic milk jug made from petroleum.
So if I bury that quote-unquote sugar-based plastic shirt in my backyard,
the bacteria in your soil will look at it and shrug. They cannot break those chemical bonds. It will sit there for centuries. Just like the oil-based version, bacteria don't care about the source. They care about the bond energy.
that feels like a massive loophole in the marketing. So to really understand what we're buying, we need to categorize these materials properly. The research suggests 4 buckets to keep this straight.
Yeah, 4 buckets is the best way to visualize it. Bucket 1 is the legacy stuff. Fossil-based and non-biodegradable. That's your standard PET, polyester, nylon.
The stuff filling up the landfills, the status quo.
Exactly. Bucket 2 is a bit of an anomaly, and frankly, I didn't know much about this until we dug into the research. It's fossil-based, but biodegradable.
Wait, oil-based plastic that actually rots?
Yes. There are synthetic plastics, specifically things like PB8 or PCl, that are derived from petroleum but actually have a chemical structure designed to break down. They are quite rare in fashion, but they do exist.
Okay. And bucket 3?
Bucket 3 is what we just discussed regarding the sugarcane plastic. Natural-based, but non-biodegradable, so your bio-PE, bio-PG.
Which leaves bucket 4.
The holy grail. Natural-based and biodegradable. This is where we find the materials everyone is so excited about. PLA, PHA, and starch-based polymers.
Before we get into the specific acronyms of those grail materials, I want to touch on the mechanism of degradation itself, because I think people imagine biodegradable means it just vanishes into thin air like magic.
Right. No, it's a biological digestion process.
Sure.
Microorganisms, bacteria, and fungi literally eat the material. But the environment where that happens is absolutely critical.
How so?
Well, if it happens in the presence of oxygen, we call that aerobic degradation. The result is CO2, water, and biomass. That's what happens in a well-managed compost pile.
But most clothes don't end up in a nice compost pile. They end up deep in a landfill, buried under tons of trash.
Correct. And there's zero oxygen down there. That's anaerobic degradation. And that is a significant problem because the byproduct isn't just CO2, it's methane.
And as we know, methane is a greenhouse gas that is significantly more potent than CO2.
Exactly. Context is everything. A biodegradable spoon in a landfill is potentially worse for the climate than a standard plastic one that just sits there doing nothing.
That is a very sobering thought. Let's meet the actual players in bucket 4, though, because we clearly need alternatives. The one I see most often in the data is PLA, polylactic acid.
PLA is definitely the market leader right now. It's made by fermenting starch or sugar, usually from corn, sugarcane, or even food waste.
Why is it the winner so far? Is it just cheap?
It's relatively affordable compared to the others, yes, but it also has really good textile properties. It has a silky sheen, it feels soft against the skin, and it breathes pretty well. But reading through the limitations here, it kind of has a split personality.
In what way?
Labeled biodegradable, but it's very picky. If you throw a PLA shirt into the ocean, it barely degrades at all. The ocean is just too cold.
Wow.
And if you throw it in your backyard soil, it might sit there for a very long time. It really requires industrial composting conditions. We're talking temperatures around 60 degrees Celsius and very high moisture just to break down in that 30 to 45-day window.
So it's not exactly nature-ready in the wild. It needs a facility.
Not entirely, no. Plus, mechanically, it's quite brittle. It has low breaking strength. You definitely wouldn't want a climbing rope made of pure PLA. In clothing, it's often blended with other fibers just to make it durable enough for daily wear.
Okay, so PLA is kind of the good enough for now option. What about the next generation? The notes mention PHA and PHBV.
Oh, these are fascinating because they are true biopolymers. They're produced actually inside bacteria.
Bacteria are manufacturing the plastic.
Yes, the bacteria store energy as these little granules of plastic inside their cells, almost like how humans store fat, and then we harvest those granules.
That is incredible. What's the advantage over the corn-based stuff?
Their absolute superpower is biodegradability. PHA is one of the very few bioplastics that can actually degrade in marine environments.
Which is huge for the ocean microplastic problem we mentioned earlier.
Exactly. Plus, it has natural antimicrobial properties.
So marine degradable seems like the gold standard given the pollution stats we started with. Why aren't we all just wearing bacteria-grown shirts?
Economics and physics mostly. They are very expensive to produce right now, and much like PLA, they are mechanically weak. They just aren't very strong. So again, you usually see them blended with something else to get a usable fabric.
It seems like there is always a trade-off. Now, we also have those fossil clones, the bio-PE and bio-PP we mentioned. Why would a company use those if they don't biodegrade? Is there any benefit at all?
It's mostly an infrastructure play. These are what we call drop-in replacements. If you run a massive textile mill, you don't need to buy new looms or extruders. You use the exact same machinery you already have. You're just feeding in a raw material that came from a plant instead of an oil refinery.
So the benefit is strictly regarding carbon reduction at the source.
Yes. PLA and bio-PE can actually have a negative carbon footprint during production because they absorb CO2 while the plants are growing. Standard plastics obviously emit massive amounts of CO2.
Yeah.
but you are still left with a piece of plastic that lasts 500 years.
Let's pivot to the user experience for a second, because I don't care how eco-friendly a shirt is. If it feels like wearing a garbage bag, no one is going to buy it. How do these materials handle the sweat test?
Surprisingly well, actually. You might assume plastic clothes are inherently sweaty, but the data shows PLA is actually more breathable than standard polyester or nylon.
Really? More breathable than polyester?
Yes. Its molecular structure allows for higher moisture vapor transmission. It's not quite cotton. I mean, cotton loves water and actively absorbs it, but PLA lets sweat vapor escape, much better than old-school synthetics.
That's a definite win for comfort. Now, looking at the safety aspect, I was pretty alarmed by the section on flammability in our sources.
Yeah, this is a serious issue. PLA is highly flammable.
More than regular polyester.
It's comparable, but the behavior when it burns is different. In low-oxygen fires, PLA generates a significant amount of smoke and toxic gas. And generally speaking, for clothing, catching fire easily is a deal breaker.
I would hope so. How are they solving that without just dumping toxic flame retardants back into the mix?
They are actually looking to nature again.
Yeah.
Researchers are developing flame retardants using lignin.
That's from wood, right?
Exactly. It's a waste product from the paper and wood industry. They mix lignin with ammonium polyphosphate. When it burns, it creates a char layer, basically a hard carbon crust, that stops the fire from spreading to the rest of the fabric.
Using wood waste to stop corn plastic from burning, I really like the circularity of that.
There's also a really smart application with viscose, which is a wood pulp fiber. They're blending it with alginate.
Alginate, is that like from seaweed?
The very same. Alginate is naturally flame resistant, so you mix seaweed into the wood fiber and suddenly your shirt is much safer, entirely without using harsh chemical retardants.
Okay, so we can make it safe and we can make it comfortable. But the sources for this deep dive didn't stop at just making fabric. They went into some really heavy high-tech applications.
They did.
And this is where I want to slow down a bit, because some of this sounded like pure science fiction to me. Let's talk about 3D printing on clothes.
Right, so this is a technology called FDM-fused deposition modeling. The core idea is to print a rigid pattern, a logo, or even structural support directly onto a piece of fabric.
Which makes sense, because usually if you want a logo, you have to cut it out of another piece of vinyl or fabric and sew it on.
Yeah. Which creates scraps and waste. 3D printing is additive. You only use the exact amount of material you need. The challenge, though, is getting the plastic to actually stick to the fabric.
I imagine it would just peel right off once the shirt bends or stretches.
It often does. The source material highlights a really specific study on this. It turns out adhesion isn't just about glue, it's about chemical compatibility. PLA sticks really well to acrylic fabrics because they are chemically similar, but it absolutely hates polyester.
So the underlying fabric determines if the print even survives.
And not just the fabric. The printing speed and the temperature of the extruder are critical. If you print too fast, the polymer doesn't have time to bond with the fibers. If you get it right, though, you can create custom, durable garments with zero cutting waste.
That connects perfectly to the broader theme of cleaning up the industry. We talked about solid waste, but the textile industry is also a massive water polluter.
Oh, dyeing clothes is incredibly toxic. It releases heavy metals and synthetic dyes right into freshwater systems. But remember chitosan.
The crab shell stuff.
Yes. Beyond being antimicrobial, chitosan is highly porous. It acts like a sponge for pollution. Researchers are using it to absorb, that's what the D dyes, and heavy metals from wastewater. It basically sucks the poison out of the water so the water can be safely reused.
That seems like a massive application given the scale of commercial dyeing factories. Now, I have to ask about the glowing silk, because this sounded like a gimmick at first, something for a rave, but the science is totally legitimate.
It is very real. Scientists took silk fibers and coated them in gold nanoclusters.
Tiny clusters of gold atoms.
Extremely tiny. When you do this, it creates luminescent golden silk. Under specific lighting conditions, it literally glows red.
Aside from looking cool at a nightclub, what is the actual utility there?
Anti-counterfeiting. Imagine a luxury handbag where the stitching glows a specific wavelength under UV light to prove it's real. It's a chemical fingerprint. Plus, the gold coating creates extremely high UV protection for the wearer, and it's totally non-toxic.
There was one more technology that I think we skipped over: plasma treatment. The notes mention this in the context of hospitals.
Right, this is a huge step forward for medical safety. Usually, to make a hospital gown antibacterial, you soak it in wet chemicals. That creates toxic runoff and consumes a ton of water.
What's the alternative?
Cold plasma. You use a gas activated by electricity to coat the fabric with titanium dioxide, TiO2. It gives the fabric antibacterial properties without using any water or solvents at all. It's a completely dry, clean process.
It's amazing how many different problems are being attacked simultaneously here. But I want to ground this for the listener. We've talked about nanoclusters and cold plasma, but is this all just happening in a lab, or can I go to the mall and buy a bio shirt today?
The market is moving fast. You can absolutely buy these things right now.
Give us some examples of what's on the shelf.
Well, take leather. There's a company in Italy called VGA. They make wine leather.
Wine leather.
Yeah, they take the grape mark, so the skins, seeds, and stalks left over from making wine, and turn it into a leather alternative. It solves a waste problem for the winery and a material problem for the fashion world.
That is fantastic. I've also heard of mushroom leather.
Milo. It's made from mycelium, which is the root structure of mushrooms. Big brands like Adidas and Lululemon are heavily invested in this. It looks and feels remarkably like animal leather.
And for the outdoor enthusiasts?
The North Face actually partnered with a company called Spiber. They released the Moon Parka. It's made from brewed proteins, essentially artificial spider silk created through fermentation.
Fermented spider silk parkas. We really are living in the future.
And even shoes. Vivo Barefoot is making footwear using algae foam and corn biosynthetics. Companies like Aquafil are making bio-nylon directly from plants. The pivot is definitely happening.
So to wrap this up, we are in a transition. We have these massive problems with pollution and oil reliance, and we have these incredible solutions: corn, bacteria, wood waste, crab shells. But it feels like we aren't quite there yet.
We aren't. And the big takeaway for the listener should really be that bio isn't a magic wand. We have to constantly balance the source of the material with its end of life.
And we have to make sure we aren't just creating a new kind of waste in the process.
That is actually the final provocative thought I want to leave everyone with.
Yeah.
Think about the life cycle. We talked about how bio-PE and PLA reduce greenhouse gases when you make them.
Right.
But remember that landfill scenario. If that PLA shirt ends up in a standard landfill where there is no oxygen, it doesn't just sit there benignly, it tries to degrade anaerobically. And that releases methane.
Which is much worse for the climate than the CO2 we save by growing the corn in the first place.
Exactly. If we switch entirely to bioplastics, but we don't fix our waste management systems to actually compost them properly, we could theoretically make global warming worse, not better. The material is really only as good as the system that catches it when you throw it away.
That is a heavy thought to end on. It's not just about buying the right thing, it's about where it goes when we're done with it.
Precisely. It's a systems problem, not just a material problem.
Well, on that note, to everyone listening, check your labels, look for those biomaterials, but maybe also think about getting a compost bin. Thanks for joining us on this deep dive.
A pleasure.
See you next time.